I think we can start the last session of the day. So we have Fredrik Bakke, who will talk to us about the Cantor Schröder Bernstein theorem in infinity topoi. What is yours?
Thank you. So yes, so the Cantor Schröder Bernstein theorem is a classical theorem. You probably most of you have probably seen this before. It states that if you have two sets and they mutually inject, then they are equivalent as sets. They are in bijection. So it's a very fundamental result. I mean, if you give any sets, and if you have this very simple condition on them, that you have an injection in each direction, then you have two equivalent sets. Is a very useful way. I mean, if you want to prove that two things are equivalent, this is one simple way to do it right. And so it would be useful if you could have something similar for types. There's this there is a way to do this. You can use the law of excluded middle. So it's a classical theorem, as I stated. This is due to Martin Espardo. But I want to answer the question, well, can we do better? Can we give more general conditions for which we have equivalences? And when does it happen? So the title is, Cantor Schröder Bernstein theorem in infinity topoi. This is a bit of a sort of a pun because Martin's paper on this is called the Cantor Schröder Bernstein theorem for infinity groupoids. I'm not actually going to talk that much about infinity topoi, but the point of the project here is well, we're looking for generalizations that applies. We don't actually need infinity topoi. The arguments I'm going to present work very generally. This should really work in most formal systems. Yeah. So this is a small ongoing project I'm doing on the side, sort of. So there will be a lot of questions at the end. It's not finished. Okay. So a little bit of history. This theorem was first stated in 1887 by Cantor, and then proven the same year by Bakke, using only the law of excluded middle. About a decade later, Cantor proved it with the assumption of the well-ordering theorem. And then the first published result using only the law of excluded middle was by Bernstein. And more recently, in 2019, Fredrik and Brown shows that, well, you can actually deduce the law of excluded middle from this theorem. So we can't deduce the general statement for all types if they inject into each other, then they're equivalent, because that would not be intuitionistic. Yeah, and then a year later, Martin shows, well, you can do it for infinity groupoids. And then 2 years ago, Forster, Jan, and Smolka, they give an entirely axiomaless construction for a limited class, namely the Beach-Ax of natural numbers, under sort of the umbrella of this constructive Cantor Schröder Bernstein theorem called the Mayer-Lawson isomorphism theorem. But you want something more general. Okay. So let's revise the statement again. So if you're given two sets, A and B, and they mutually inject, you have sort of a diagram like this. You have your set A on the left-hand side and your set B on the right-hand side. And then your injections F and G, they carve out images into the domains like this. But these aren't necessarily surjective. In general, they may not be, even if you have this mutual embeddings. And so we need to correct for this. We need to construct some new map that actually is a bijection. So how do we do this? Well, we'll revise a proof by Koenig very shortly. Well, very quickly, I mean. So again, you have your injections, F and G. Well, the observation we're going to use is that if you have some element of A, well, by the law of excluded middle, you can decide if there's a preimage under G, since it's necessarily unique, you can apply the law of excluded middle. And the same, if you have the preimage of G, well, then you can decide again if there's a preimage of F, so you can backtrack along these injections you have. And so we can form a chain maybe infinite, maybe not. Maybe at some point there is no pre-image that looks like this. And we say, if this chain satisfies a particular condition, namely that if you're given some pre-image of F in this chain, well, you can actually go one step further. You can find a pre-image of G for it. Then you call X a perfect image for G relative to F. Okay, and then with this definition, we define a new map. It's call it H, and it says that, well, if you have a perfect image, well, and in particular, it has to be a pre-image of G, so you can use that. Otherwise, we use F. So you go forward with F or backwards with G. We split depending on if we're in the perfect image or not. So again, we've used the law of exclusion middle to decide if something is perfect or not. And then we can do some case analysis using the properties of the perfect image and show that this thing is actually an equivalence. And so we're done. Okay, so we've done a classical proof of the theorem for sets using injections, but then how can we now generalize this to type theory? Well, first of all, having unique pre-images is a common assumption in type theory, namely being an embedding. So we can just replace the injection condition with being an embedding, which is a stronger condition. But classically, they coincide. And this was the observation by Martin. So that's the basis for his paper. Okay, you can just swap this assumption that things are H sets for having embeddings, and you're done. Okay, and then we need to decide if F and G have pre-images, but we can just add this condition locally. You can ask that the F and G actually make decompositions of their codomains so that you can tell if you're in the image or not. And then finally, we have to somehow decide if we're in the perfect image. And for this, we're going to use a constructive taboo called the weak limited principle of omniscience, the WLPO. Okay, so we've just done a simple analysis, and we've identified the problems with the current proof, and here are the remedies. So let's talk a little bit about the WLPO, and then I'll give the new statement. Okay, so the weak limited principle of omniscience, well, it has many equivalent forms. So maybe the most simple statement to give is that if you have some decidable subtypes, you can decide if something is in the subtype of the natural numbers, then you can actually also decide if this subtype is full. A different equivalent definition is that, well, you can decide if you have any binary sequence of the natural numbers is constant. You can also, it's equivalent to asking that this co-natural numbers, the one point of compactification of the natural numbers, is if it's decidable, if you're at infinity or not. And finally, the condition that we're going to use is that that is used in the proof is if you have some family of decidable types, it's no longer necessarily unique points over every natural number, then you can actually decide if there's a section in this family. So where does this occur? So this is where like the infinity topoi come in, like which models do you see the weak limited principle of omniscience? And in some sense, this is it's an anti-topological axiom. Like it really axiomatizes that you have discontinuous functions. So some of you may have heard this statement that, I mean, every function is continuous in type theory. And this is sort of like a first step to saying that, well, we actually have discontinuities. But this is in a different sense than like homotopical discontinuity. This is really in a topological sense of the word. A different way to understand it is as a sort of a solution to the halting problem. Like you can decide if a machine on the natural numbers terminates or not. Okay, so where do we place it in the landscape of other classical axioms? Well, it's right there. So the locus through the middle implies the weak limited principle of omniscience, but in general, it's weaker. In fact, it's also weaker than something called the De Morgan's law, which states that you can just, well, negations of propositions are decidable. It's the easy way of saying it. There's also the limited principle of omniscience, which is a bit stronger, and we have something called the lesser limited principle of omniscience, which is a bit even weaker, and then there's a lot more nonsense if you go in even further down this this rabbit hole here. Yeah. Okay, so what can we conclude? Well, if you just assume this axiom, weak limited principle of omniscience, well, and your maps G and F are embeddings whose fibers are decidable, then your types A and B are equivalent. But actually, we can say something stronger. Even if F is not necessarily a decidable embedding, you can conclude this, that if its fibers are merely decidable and the fibers have double negation dense equality, meaning that this equation holds, then B is already a retractive A. And so one particular example of this is that if F is some sort of co-product of a connected map together with some component that it does not hit, then F is a map that satisfies this condition here. Okay, we can say something a little bit more general still. We can also omit the weak limited principle of omniscience if we somehow were already able to conclude that our image our perfect image gave a co-product decomposition of A. And so there's this even more general condition here. You can ask that G is just a double negation stable embedding, and the fibers of F satisfy this particular property that if you're given some family over its fibers that is double negation stable, then in fact, if you have the double negation of this thing, then you can already construct an element in this family. So it's a bit a technical assumption, but still it's more general. Then you can deduce that A and B are equivalent using the very same construction. So, I mean, this gives an answer, right? I mean, you can, this is a completely constructive proof, but I mean, there's a very particular thing you're checking, right? You're checking if the perfect image is decidable or not. So it's not very satisfactory still, I think, but it's constructive. So there you go. We can also look at other approaches. You can try to, instead of restricting the conditions on the maps themselves, you can try to restrict the classes. That's what Forster, Jan, and Smolka did, and we can give some extensions to that. So we have a theorem for finite types, where this proof will work for most notions of finite type. Then, with no further conditions, you just have embeddings between A and B, then they are in fact equivalent. And what I mean by most notions is that it can be any of these things. So Bishop finite means it's equivalent to a finite type, a standard finite type, I mean. It can be subfinite, meaning it's a subtype of a standard finite type. It can be finite the index, meaning it's a quotient, meaning there's a type and you have a standard finite type and a surjection onto this type. So in particular, that applies to pi finite spaces. It can be a subfinite the index, which is even more nuanced. And then we have the thing at the bottom here, which is a Dedekind finite type, which is what I'll show the proof for. So Dedekind finite type is a type such that every self-embedding is an equivalence. So you can already see there's surely some connection to the Cantor Schröder Bernstein theorem here. And indeed, we can give a very slick proof using the 642 property of equivalences. So if you have your embeddings from x to y called f and from y to x called g, well, we can form this diagram here. And the top and bottom rows are equivalences by Dedekind finiteness. So by the 642 property, the diagram is just a diagram of equivalences. So in particular, x and y are equivalents. Okay, so that's sort of the positive answers I have for you today. But there's lots of more to explore. I mean, I gave some questions in my abstract or conjectures in my abstract that I haven't answered today, but I'm hoping to do it. So let's discuss it a little bit. So I gave this construction that can give you retracts between A and B, given all of these technical assumptions. So the question is, well, are there examples of this, non-trivial examples? I don't know. I don't have them yet. Can we give it an entirely axiomalist proof? So this is something I conjectured in the abstract. I mean, there I also assume function extensionality, but I haven't used that today. So these are free of function extensionality. So one possible way to do this is to look at trying to change the definition of the perfect image. And I've made some attempts at this. I mean, trying some sort of co-inductive definition instead. It hasn't really panned out yet. Not saying it doesn't. Could also look at other proofs. I haven't reviewed the entire literature of proofs of this theorem, but there's quite a bit of it. So could be a proof out there that really just sort of lets you go to town. Of course, I mean, it's very important here that we're only relaxing the assumptions in A or B. We still need some sort of causicality in there because of Fredrik and Brown's counter proof, right? Well, you have to have something that encodes the law of external middle in your theorem. So you have to bake it in somehow with what are the minimal set of assumptions here. Have to bake in, right? For Sjan and Smolka, they give this axiomless construction for retracts of natural numbers. Does it work for other types? I mean, one potential solution I imagine could work is that you could replace natural numbers by any ordinal. I don't know. Pure conjecture. We'll see. And finally, I mean, there's a dual Cantor-Schröder Bernstein theorem saying that if you have two sets and surjections between them, then they are in bijection. Is there an equivalent in homotopy type theory for this, where we replace surjection by epimorphism? So that's another question I'd like to answer. Or if any of you have ideas, let me know. All right. So I don't know how I'm doing on time, but that's sort of all I wanted to say. So everything I've said is formalized. Some of it's in type topology, some of it's in Agda Unimath, but it's not public yet. But in conclusion, I mean, this is a very fundamental theorem. It's a way to prove that things are equivalent. We want to do this very often in type theory, so it would be nice to have this. And what are the most general assumptions we can add? Okay, thank you.
Okay, so we have quite a bit of time for questions.
Sorry, so in the results about finite types, do you prove them as special cases of your more general theorem, or are they, like, for example, do you prove that in these cases you have the assumptions of your other theorem?
So,
or do you prove this?
Everything here implies static infiniteness, and so we just have to consider the case of static infiniteness. Yes.
Okay, and then the other theorem.
Sorry.
For static infinite, the other theorem applies. Like this becomes a special case.
No. So this is a completely different proof, right?
It's completely different.
So here's the conclusion, right? We don't need the perfect images at all, right? You have the 6x2 property for equivalences, and by the dedicant finiteness, you can just conclude that you have an equivalence. The type maps are already equivalent.
Okay, sorry,
I
forgot about that. Yeah. And then the second question: what is pi finite? How do you define it again? You said it, but
so I mean, well, it's so you have you take the zero truncation of your type, and you ask that this is a Bishop finite. So I mean, this is actual equivalence to a standard finite type. And then inductively, at every higher level, you ask if this is still true over every base point, and then it has to terminate at some point. Yeah. But I mean, this also applies to like unbounded pi finiteness. You just need that the base layer has an indexing.
Question?
Yeah, I assume that neither proof applies to finite CW complexes.
I don't know. I haven't inspected this. I mean, no. So how do you define a finite CW complex?
It's built up as a CW complex in a finite number of steps.
So, and you have finite stalls at every step as well.
Yes.
Yeah, well, so there's one step in this proof I haven't checked. So it could be wrong, and that's so you need something called the finite choice for this simplification down here. And if that only applies to sets, well, then indeed you need to add the assumption that everything here is a set as well. So that would be set level pi finite types, which is not very interesting, is it?
Right.
So okay, there's I could be wrong. Yeah, it's true.
I just had a small comment. So you mentioned the work by Yannick Forster and small Cantor, where they use the retracts of n, where they use a.
Oh yes, they use discrete enumerable types, and then they show that this is equivalent to being a retract of natural numbers.
But they don't define retract in the usual sense.
Oh yes, so they go into like the option type, right?
Yeah,
yes.
Exactly. So have you thought about what happens if you define retract in the usual sense?
Is this not equivalent?
I don't think so. Maybe for natural numbers, but not in general.
Yeah.
Because you get like some fallback argument. I mean, we could take that one.
Okay.
Can you say one more word about why you call this thing anti-topological at the beginning?
Oh yeah. I mean, so it's really like it rules out like topological toposes, like toposes where maps are continuous in some topological way. So like for instance, let's say this. Yeah. Yeah, I mean, it really, this is like I guess in the way the community understands what the topological topos is, I mean, that you should understand the object as being topological in some way. So yeah.
Okay, and what was that comment about the halting problem? Like,
oh yeah, I mean, I'm just throwing out, intuitions that I hope people can latch onto. I mean, it's sort of like you should be able to decide if some process halts. This is essentially the content of the weak-limited principle of omniscience. So in our proof, we're trying
the second statement on the slide. This
the halting problem. I mean,
it's the one that you're referring to.
I mean, you can understand this. I mean, at some point, it's going to be. I mean, if you have some sequence that bifurcates up and down, you should be able to decide if it at some point stabilizes and then continues to be constant after that. That's one way to understand it.
I mean, the simple way to determine it is you can write that as you can write the number of steps the Turing machine runs as a connatural number, and so you use number 3 there.
Okay.
Okay. Any more questions? No. Then we can thank the speaker again.